already, and hopefully everybody was aware of that. It seems so. So I'll be talking now about, more specifically, the Parrinello method, and in what sense it's different from Born-Oppenheimer dynamics. I'll go through a number of things about parallel implementation and efficiency, and finally I'll try to show an example of application. So let's start with the Parrinello method. Parrinello molecular dynamics was actually historically the first form of ab initio molecular dynamics. Born-Oppenheimer was really used later, and one reason is that it's a little bit more expensive computationally to do Born-Oppenheimer molecular dynamics. And initially, what Carr and Parrinello were doing, the first time was in 1985, and keep in mind that back then, the fastest machine they had access to was a Cray 1, which is something that was boasting something like 40 megaflops, or something that is way less efficient than your laptop. So at the time, issues of efficiency were really very important in enabling these methods. So the main idea behind the Parrinello method was to evolve the ions and the electrons simultaneously. So it means not in the way we do it in a Born-Oppenheimer approximation, where we do the electrons and then do the ions and then do the electrons again, but really merge the two loops into a simultaneous evolution of both. What is the justification for doing so is basically based on the assumption that electrons will remain close to the electronic ground state when we do that during the time evolution. And I emphasize close because here we don't really assume they're going to be at the ground state at any given time, but that they will be nearby the ground state. And the way that is done is by using a second-order dynamics for the electronic degrees of freedom, which is kind of the same kind of dynamics we use for the ions. Newton's equation for the ions is a natural way to do things. It's a real physical way to do things. But a second-order dynamics for the electrons is not a natural thing to do. We just now artificially consider the electronic degrees of freedom to be classical variables in a sense. And that means that we can use now some kind of fictitious Newton equation for the electronic degrees of freedom. The natural way you would want to do time evolution for a Schrödinger equation would be a first-order dynamics with a complex wave function, which is what really the time-dependent Schrödinger equation is. So this is really a different type of dynamics. There's no, in principle, no physics associated with the dynamics of the second-order dynamics in the Parrinello method. So if we're going to use second-order dynamics, then we also have to assign a fictitious mass to the electrons, to these degrees of freedom that describe the wave functions. And we'll discuss a little bit later what that is. The questions that we have to ask if we want to use this approach is, first of all, what does this fictitious mass mean? How do we choose it? Second is, if we now only assume that the electronic wave functions will be near the ground state and not exactly at the ground state, the question arises as to what's the accuracy of the forces that we're going to derive from these. We have wave functions that are not exactly eigenstates of the Hamiltonian, and therefore when I compute forces on nuclei from these wave functions, you might ask, how good does it be? And finally, also, there's again this problem of keeping these orbitals orthogonal. And the second-order dynamics in general will not preserve orthogonality of wave functions. And we have to restore this orthogonality. And the way this is done in the Parrinello method is really the main feature that made it possible for Parrinello to implement that is to enforce this orthogonality by using the concept of polynomial constraints on the wave functions, this time not on the nuclei. So again, this is what we're dealing with, our Croncham equations, and we now are going to do the evolution of the phi I using the kind of Newton dynamics. And we're going to have to deal here with this orthogonality constraint. So So how do you implement second-order dynamics? Well, we do the same that we do for the nuclei. So in that sense, we're going to be just computing a Vertex step now in the wave functions. Okay, so this is what would happen if you just forget about the constraints for now. So this is reminiscent of what we did in the calculation for the constraints on nuclei. So you would compute the wave functions at a time t plus dt by using the Vertex algorithm here. And so we have twice the wave functions at the current time step minus the wave function at the previous time step. And now we have here what would be the equivalent of the acceleration in conventional Newton dynamics, delta t squared divided by the mass. Now this is this fictitious mass that I give to my electronic degrees of freedom. And the force here is really the Hamiltonian applied on the wave function. It's basically direction that minimizes the energy, so it's the same as the gradient of the energy in the case of the conventional dynamics. So what happens if I just use this expression? Well, I can compute the wave function at the next time step, but in general, it will not be orthonormal. This is the way we can convince ourselves that orthogonality is not preserved by these dynamics. Start from two wave functions, simplicity, which is assume we have two wave functions, and assume that at time t they are orthogonal, and at time t minus dt they were also orthogonal. And now let's compute the new wave function. And now if I compute now the scalar product, I do that for both wave functions. And I compute this scalar product between the two new wave functions here. You will find some cross terms that involve the previous times, and those will be okay. But there will be the cross terms involving the Hamiltonian, and those will in general be non-zero. So in general, the orthogonality will not be conserved by Berle dynamics. So we'll use the same idea that is used in constraints in molecular dynamics to enforce these constraints. So the way it looks is this way. This is the formulation in which we have Lagrange multipliers here, organized as a matrix lambda ij. And the effective force that's acting on the wave function comes from the Hamiltonian, but also from the constraints. Okay? So the calculation will now have to specify, or we'll have to figure out what these Lagrange multipliers are, the lambdas, in order to preserve the constraints. So if you look at this equation and try to think of how you would implement that, one possibility would be to try to figure out at a given time what those numbers are, and then integrate the equation to do one step in the future. But that doesn't really work, because no matter how well you do your integration, there will be a small error after one step that will make these functions non-orthogonal. So it's the same as in the case of the classical dynamics. We don't really enforce the constraint right away. We first do a unconstrained step where we neglect the constraints, and after that step we restore them exactly. Okay? So this is the way the Parrinello algorithm works. So in practice, what is implemented is that you first make a step of the Berle iteration, ignoring the constraints of orthogonality, so you get a set of wave functions phi tilde, which are not orthogonal among each other. And then you find an algorithm, and we're going to discuss that now, that will bring you from these non-orthogonal functions to a set of orthogonal functions at t plus delta t. Okay, so we don't do it right away to enforce the orthogonality. We ignore it first and restore it later. So now the question is, how do we do this restoring of orthogonality? And so there's really a parallel here between the way it's done in classical MD and in the Parrinello method. And it's actually no surprise. This is really historically how it came about, because Roberto Carr, being really an expert in electronic structure at the time, and until now, of course. And Michele Parrinello really coming from the world of classical molecular dynamics and being an expert in how to deal with constraints. And there came the idea of putting the two together and getting Parrinello dynamics with constraints on the electrons. So again, as in the case of the molecular dynamics, there are different ways of restoring orthogonality, like there are different ways of restoring a constraint. And in this case here, you could just apply the Gram-Schmidt algorithm on your wave functions phi tilde and recover orthogonal wave functions. Now, you could also use what's called Lövdin orthogonalization, which is something used mostly in the world of quantum chemistry, which is a different transformation, which uses a calculation of an overlap matrix and computing the square root, or the inverse square root of that matrix. So it's a little bit different algorithm. Also gives you, in the end, a set of orthogonal functions. So there are all kinds of different ways of getting that. But there's only one way that corresponds to a holonomic constraint. So again, we will find what is the algorithm that will restore orthogonality among wave functions in a holonomic way. Okay? So again, holonomic constraints are defined to be such that the constraint force does not perform work, so the velocities of the constraint force are orthogonal. And the consequence of that is we can only correct the wave functions phi tilde by adding to them linear combinations that are in the subspace of the solutions at t. Okay, so notice at t plus dt we'll have to add corrections using the functions at t. Okay, this is what the holonomic constraint forces us to do. Okay, so let's see a little bit of the math of what that means. Again, matrix notation, that's our usual matrix Y with all the Fourier coefficients of our wave functions in it. M rows here, number of basis functions, number of plane waves, and here the number of wave functions. And so first of all, using matrix notation, for all my wave functions, I compute the new non-orthogonal wave functions. That's t plus dt, using the Verlet algorithm here. So it's just a compact way of expressing that in matrix form with all wave functions at a time, at once. And now is the correction to get the constraints back, get the constraints satisfied. I will add to y tilde the correction that is in the subspace spanned by the solutions at t. Now, it can be any arbitrary linear combination of these functions. That's why there's a matrix X here, which is an n by n matrix, only number of states by number of states, that can mix these arbitrarily to restore the orthogonality. Okay, that's what I'm allowed to do. So then the question boils down to how do I compute the matrix X such that these functions here will be orthonormal. So to do that, I write the orthogonality condition at t plus dt. So I take the expression I had here, which is my corrected matrix, and transpose it, multiply it by itself. Yes?
Is it obvious why the correction is in the space of the previous time step?
It needs a little bit of algebra, but this is the definition of holonomic constraint, basically. If you look at what the velocity would be and the force, and you impose this condition that you don't want the force of constraint to work, that would be what happens. I'm not elaborating on that here. So now I'm expressing the fact that I want these wave functions to be orthogonal at t plus dt. So this is what it means. My corrected function times the transpose here must be the identity matrix. This is the way of expressing orthogonality of the columns of the matrix Y. So now I have to distribute these products here. So I get y tilde transpose y tilde, and then this transpose is going to be a reversed product of the matrices transpose, and so on and so forth. So a little bit of matrix algebra here. So I get the following line here. So that's a matrix equation, right? these matrices here, each one of those terms is an n by n matrix, number of states by number of states. Even though some elements here, this is a different matrix, it's n by n. But this transpose this is an n by n matrix. Okay? But I get all these terms here, and now I give names to some of these products here. Okay? And I notice here also that the matrix Y, which is the one at the time step T, is orthogonal, so therefore if I compute Y transpose Y, this is the identity. So basically what I get is this equation here. That's a matrix equation I have to solve, and that's actually an algebraic Riccati equation. It's actually interesting to see that this was not recognized by Parrinello, and they sort of wrote that equation and solved it, but they were not really in touch with the numerical analysts who do numerical linear algebra, and it was only much later that it's recognized that this is actually an algebraic Riccati equation. It was known in the world of control systems. So people building robots and trying to determine the stability of feedback systems are dealing with these equations. But then it was sort of discovered separately in electronic structure, completely different context.
So the wave function components denoted by a Y matrix should be in a complex complex matrix, or real number.
Yeah. So I'm writing transposes here, and it's just for real wave functions. But all this applies to complex wave functions as well. So you would have permission transpose here, and it would be
Actually, it is complex, right?
Well, it depends. I mean, there's some situations where you can have real wave functions. I mean, if you use plane waves and you are at the gamma point, then you have real wave functions. Or if you use an isolated system and you have real wave functions, it's possible. But just to simplify, I'm dealing with those matrices as real matrices. It doesn't really change the argument.
Excuse me. As you said that this equation was not noticed and used in the robotics and other places. Here we are talking about the molecular dynamics of molecules and so on. What is the commonality? Do you find really any connection? Why this same equation would be there? Also same equation should work here.
I don't think there's any simple connection between that and control systems. I mean, the way the algebraic Riccati equations appear in control systems, I don't think you can draw a parallel. I mean,
Until there is some universality or some connection.
Well, I guess, the common point would be that whenever you study the perturbation of an eigenvalue problem, you can actually show that there is underlying there's an algebraic Riccati equation. But, beyond that, I'm not sure there's more than that. So basically, this is in the end the problem we have to solve. We want to restore that orthogonality condition. And remember that in the case of the shake algorithm for the constraints on the ion, we had this nonlinear equation we had to solve, which was the nonlinear matrix vector equation. Well, here it's this equivalent here. It's also a nonlinear equation. You have a quadratic term here in terms of that unknown x, and we have to solve this nonlinear matrix equation now to get our constraints right. So how do we solve that? Looks like I have twice the same slide here, so let's skip to the next. So the way we solve this equation here is just by using something that's very general. It's called the fixed point method. And the fixed point method basically is a way of solving a nonlinear equation for a function f of something that's x here. You want to solve f of x equals 0, assuming you're not too far from the solution. And the way that works is that you define another function g of x, which is defined to be x plus f of x. It's pretty simple. And then you basically compute g of x at your current guess and define that to be your next guess. And you repeat that again and again. Okay. And at some point, if that converges, you can convince yourself by looking at that, that will mean that f of x is 0. The question is, when does it converge and why would it converge at all? Okay. Now, and there are conditions for that we can verify. Basically, technically it would mean that the function g of x has to be a Lipschitz contraction, which is a complicated way of saying that the derivatives of g of x are not larger than 1, basically. But the nice thing about this method here is that it's very general. It works for a scalar function. If you have a function of just a single variable and you're close to a solution, you can use the fixed point iteration to solve it. But in fact, the theorem about the fixed point method are really so general that they only ask you to have a function defined on a Banach space. That's kind of really very general object. So it means in particular that for vector functions of a vector, mapping a vector onto another vector, this can work. And in our case, we're going to use that for a matrix function of a matrix. Okay, that's what we had before. We had this here. That would be our function f of x, which is a function of a matrix x. Okay, it's a complicated function of a complicated object, but the fixed point method works even for that. And that's what we use to solve the Riccati equation associated with the Parrinello method. So basically, we define this function f of x. Now, this is factor 1/2 here in front of what we had before. And the reason for the presence of this 1/2 here is to satisfy this condition of convergence. That's a way of limiting the amplitude of the derivatives of this function. The function g, that would be x plus f of x, here is slightly different. I'll write it in this form, which enforces the symmetry of the solution. So this is another trick. We want to solve this equation with the fixed point method, but we want to make sure that we get a matrix x that is symmetric. So this is, in the end, the iteration method. So that's easy enough. Compute this product of matrices, add this term, and that's your new matrix. Okay, and repeat that until it converges. This is what's implemented in the Parrinello method. Now notice that maybe at some point you have to stop that iteration in the fixed point method, so you have to define some kind of criterion for convergence and what possibilities to have the 2 norm of this difference of 2 matrices. That would be the same as the Frobenius norm that we talked about earlier, and have some kind of number, epsilon, that they decide if these 2 matrices differ by less than so much, then that's enough. That's good. Now notice again that as usual in iterative methods, when you compare the difference between 2 successive steps, that doesn't give you an error bound. It could be that this difference is small, but we're still far away from the solution. So in particular, we don't know how far we are from the correct answer. But that's a general statement about iterative methods. In practice, it turns out 2 to 5 iterations are usually enough in the Parrinello method to get back to this solution x. So once we have this solution x, step back a little bit here. We're going to use it in this expression here. We can multiply x by y here, the matrices, that one we know, and correct our first guess that was not orthogonal. And we have now a set of orthogonal functions at t plus dt. So we have completed our molecular dynamics step. We started with an orthogonal set of functions, and we ended with a new orthogonal set of functions. Okay, so this is basically what the Parrinello method does. Enforcing holonomic constraints on wave functions to keep them orthogonal. A little bit of matrix algebra involved in the back to implement that, just as in the case of constraints in energy. Let's go back to the question of this fictitious mass that we use. How do we actually choose this parameter, and what does it actually mean? We have this number there that has the dimension of electronic mass, but it's not the mass of the electron. It's not the physical mass of the electron. It's a number that's usually multiple of the electron mass, and the meaning of it is not physical. It's just a numerical parameter that we use to enable the simulation. One property of it is that if you let this number go to 0, that means that the oscillations of the wave functions around the ground state will get faster and faster, and also it will oscillate closer and closer to the ground state. And it has been shown in that paper, which is actually coming much later than the Parrinello paper, by some mathematicians here in Germany, who studied the Parrinello method with all the rigor that mathematicians like. And they were able to show that if you let mu go to 0, then you get the adiabatic limit. And that's a good thing. But they also were able to show that the deviations of your wave functions with respect to the correct ones are of order mu 1 to the 1/2 square root. So when you have a small parameter in a problem, and you tend to the right answer when the parameter gets small, it's nice to have it, linear or quadratic. But the square root is not very nice. It's not the nicest convergence to the correct answer that you can think of. But that's what it is in this case. So it's a little bit of a warning that we have to be very careful when you choose this parameter, especially that the way it can affect the dynamics on the solution is quite singular for small values, so it has to be checked very carefully. So another thing is that the choice of the parameter mu and the choice of the time step are actually related. You can't choose them independently. Basically, Parrinello dynamics will mostly depend on the value of the ratio dt squared over mu. Now remember that when we were looking at the Berle algorithm here, when we compute this non-orthogonal wave function at time t equals dt, here is the number that multiplies the Hamiltonian times y. So this is really the parameter that's relevant for the stability of the dynamics. And if that number is too large, then the Berle integration will not be stable. This is, by the way, the same problem you would have if you wanted to use classical molecular dynamics to integrate the motion of a very tight bond. So suppose you have the hydrogen 2 dimer, has a very tight bond, and you want to use a time step that's too large. Okay, at some point, if the time step is too large, then the dynamics would explode. It will not be a stable integration. So the same thing would happen here for the electrons if that ratio, delta t squared over mu, getting too large. So basically, if you change mu, the time step should also change proportionally to mu to 1/2 to keep that ratio constant. And what's the largest value you can afford for that number? That's going to be limited by the energy cutoff that you choose for your plane wave basis set. So the larger the energy cutoff, the smaller the time step will have to be in order to have stable integration of the Parrinello equation. So anyway, so in the end, it means that whenever you run a simulation using the Parrinello method, you'd better make sure you check that your value of mu is not affecting your results. And that means often that you really want to repeat your calculation with a smaller value of mu, meaning also a smaller time step, and redo everything so you make sure that the physics that you learned from this simulation is not affected. Okay, well, that's just a practical aspect of it. The way it's done in QBox is basically by setting the wave function dynamics to ND. Yes?
In practice, how affected is the time step extrapolation to mu equals 0 by the singularity that's there?
Well, the extrapolation still behaves well. The extrapolation is still basically of order, is linear, the extrapolation. But the deviation of the trajectories for longer times, your time step becomes smaller also. But the extrapolation is still a linear extrapolation. It's not that it depends on the time step to the 1/2, it depends on mu to the 1/2.
But you also
So in time, you still have a linear extrapolation.
Right, but you said that you choose your time step roughly like mu to 1/2.
Right. If you reduce the mu, then you will have to reduce the time step, like the square root of mu. Yes. Okay, so in the case of QBox, then this fictitious mass is actually chosen automatically by the code to make sure that the evolution is stable. So what it does is actually defines mu to be this number, which will always make sure that the integration is stable. But it doesn't guarantee that mu is small enough to get the good physics. Okay? So if you run CP or Parrinello dynamics with Q-box, you don't have to worry about the stability of the integration, but you still have to worry about the fact that the mu that was chosen is not too large. Okay? So you still have to repeat your calculation with a smaller time step, which will then choose a smaller mu and see if the physics is the same. Okay. Now, one thing you will have to monitor carefully during the simulation is the value of the fictitious kinetic energy of the electron. So this is not the kinetic energy of the electron in the Kohn-Sham sense, the expectation value of the Laplacian. It's the kinetic energy in the classical sense of the electronic degrees of freedom. And that one is printed as this tag here. So you want to just also follow that. And your simulation in general will be meaningful only if that kinetic energy is very small compared to the other kinetic energy of the ion, the one that really represents ionic motion. You don't want to have a situation where you have the same order of magnitude of ionic kinetic energy and electronic kinetic energy, for instance. This one should be very small. So this afternoon, actually, in the lab, we're going to try running some Parrinello dynamics on a small problem with different choices of time step and see how that affects the dynamics compared to the Born-Oppenheimer dynamics. Well, the other thing, obviously, you want to check carefully is the conservation of energy, and that's what I was just saying before, that the kinetic energy, the fictitious kinetic energy of the electrons is much smaller than that of the atoms. When does that work well? Well, Parrinello dynamics works very well in the insulators when there is a gap between the HOMO and LUMO of the system, or the last occupied state, first unoccupied state. And that's actually necessary to make sure that the method is stable. This has been discussed in quite some detail in this excellent paper by Pastorius, Francois, and Buda, who made a kind of a more careful analysis of the stability of the algorithm in 1991. And they were able to show that this presence of the gap is actually necessary to be able to use Parrinello dynamics. In metals, when you don't have this gap, then things are a little bit more tricky. You have basically electronic eigenvalues that will cross the Fermi level constantly during the dynamics. Some states go above and below the Fermi level. And when that happens, whenever there's such a crossing, then this subspace described by the occupied wave functions changes suddenly. Okay? Some state is not in the subspace anymore, and another state has come in the subspace. And therefore, you have sort of discontinuous jumps in the representation of this subspace, and that's not something that the dynamics of Parrinello can track very well. We always assume that everything was smooth and continuous in time. So if you just use occupied states in your dynamics, basically you will have these states at the Fermi level that suddenly get very wrong. The state that was occupied and now should be unoccupied. Another one should come in and be different and be occupied. And you see that there are discontinuities there, and that means that it's not going to be easy with this method to track this discontinuity as states cross the Fermi level. So that's generally why the Parrinello dynamics is not used for metals. There are some developments that have been made to try to use Parrinello dynamics for metals that involve putting a thermostat on the electrons. And that's kind of a more complicated thing. I don't think it's very widely used, though. I think it's also has its problems, and it's a little bit more difficult, just because these things are the fundamental reasons why it's difficult. They don't go away. Even with thermostats, it's difficult.
Does it work well for superconductor? Because
superconductors,
because we know dirty metals are good superconductor, so it is near the insulator in some sense. So it should work.
Well, but keep in mind that superconductors are not, in principle, described by the usual functional equations. There is a principle, a density functional theory for superconductors that's a bit more complicated than the one that we normally use for just metals and insulators and semiconductors. So the that a system is a superconductor, nothing would appear in this level of theory. If you want to describe a superconductor, there are some theories that instead of the Kohn-Sham equations, you end up with what's called the Bogoliubov-Lejeune equations that describe quasi-particles in superconductors. But it's a quite different theory. So one way in which you will see Parrinello equations discussed quite often is in the Lagrangian formulation. So I'm just summarizing here the difference between the Lagrangian formulation for Born-Oppenheimer and Parrinello. So in the case of Born-Oppenheimer, it's pretty simple. You just have a classical Lagrangian, which contains the kinetic energy of the nuclei and the potential energy, which here is represented as a function of the nuclear positions. Now that's just one set of classical degrees of freedom. Now if you try to understand what the Euler equation is associated with L, that's just Newton's equation of motion, so nothing fancy here. So the potential energy, the classical potential energy here, is the Kohn-Sham energy. So it's the minimum over all possible choices of wave functions of the density functional of psi and Rh. In contrast, if you look at the Parrinello formulation, what they can do is actually formulate the whole theory as one Lagrangian. And in this way, you have, in the same Lagrangian, you have this fictitious kinetic energy of the electrons, which depends on the velocity here of the electronic degrees of freedom. You have, as before, the classical kinetic and potential energy of the nucleon. And then you have this Lagrange multiplier term that contains the constraints on orthogonality. So this basically sort of summarizes the whole Parrinello approach in one Lagrangian. And now if you compute the Euler equations that are associated with that Lagrangian, you can see up here the Newton equation as before, but also the dynamics that describes the motion of the electrons, constrained dynamics, and the fictitious mass here. So I will switch now to discussion of various items, so it's a little bit of more random things put together that have to do more with the problem of efficiency and large simulations. So first of all, let's ask why these first principles molecular dynamics simulations would become large. Why do we want to use large computers for that? I guess there are three reasons that are pretty obvious here. First of all, there's this representation of your solutions in terms of Fourier series, and those are truncated by this energy cutoff here. And the question is obviously, is that good enough, and what's the convergence of this Fourier series? So you would have to increase the energy cutoff to make sure that this is converged. That's one first thing. That will make the problem more expensive because you have more plane waves and everything gets bigger, and calculation takes longer. You also have finite size effects. So suppose that you're trying to simulate something like a liquid, and all you can afford is 32 molecules, and that's really maybe not enough to describe an infinite system. You might have correlation length in the liquid that are longer than your cell. So you have to check that you're okay for that. So you have to simulate maybe a larger system, but that's expensive too. So that's another limiting factor here. And finally, there's also finite duration. I mean, you can simulate 1 picosecond maybe, or 2, and who knows, there might be some things that happen over 1 nanosecond in your system. You're never going to see them. So you also have to check that what you observe is on a long enough period of time that it makes sense. So we need to systematically increase these things. We need to actually do all of those at once. Right? It doesn't really make sense to check finite size effect with a lower cutoff. You have to check both at the same time. So you end up with very large problems. So basically all these put together means we need large computers, and there's no way around it. We need to simulate larger systems. And by the way, when we go to larger systems, it also means we need longer time, just for the simple fact that if you lose a larger unit cell, you have more molecules in your system, the propagation of sound across the cell will take longer, for instance, meaning that the equilibration of your dynamics will take longer than in a small cell. So there are combined effects of size and time scales here that make it more expensive. Well, there's also another reason you would want to simulate faster is you want to just keep a small system or medium size, but you want to do a longer time. Okay, so that's something that requires strong scalability that we'll discuss in a minute. But also, then you might want to use better models. So you're not happy with the density functional theory or GGAs. You want to go beyond that. You want to have hybrid functions, GW, BSE, whatnot, and you want to control also the size effects in those approximations. So this is also expensive. So in the end, that means that whenever you implement these things, first principles like geodynamics and all these approximations, implementations must be parallel. There's no way around it. And they must be also scalable. And by that we mean that if we use more processors, we go faster. Ideally, if we use twice as many processors, we go twice as fast. Now there are two types of scalability that we can discuss. Right? There's one that's called strong scalability. And that is, if I want to solve the same problem with twice as many processors, do I go twice as fast? And it's the same idea as the usual story of, if you give one person can build a house in one day, it's maybe true that two people will build this house in half a day, but it's unlikely that 100,000 people will build it in 1 second. So that would be strong scalability. So this is one of the things we would like to achieve if we want to study longer timescales. We want to have the same system, we just want the results faster. And the reason it's difficult to achieve is something I'll come back to, is the fact that we have basically to perform n-cube operations, but we have only n-squared data to work on. I'll say a little bit more about that later. Now there's another thing called weak scalability, which is used in quite a few areas of computing, especially, for instance, in the fluid dynamics. And the question there is, if I want to study a system of double the size and I use twice as many processors, can I do it in the same time? So this makes sense really only in problems where the computational cost is scaling linearly with the size of the problem. And that's true of classical molecular dynamics in some limit. It's actually n log n rather than n. And in fluid dynamics, there are regimes where it's true. But for first principle simulations, we don't really have that. We have this n-cube scaling, and we have these other terms in the polynomial of the cost, so there are some n-squared terms. So it's not really easy to define weak scalability. So we usually don't talk about that too much. How do we organize a parallel plane wave code? So there I'm taking mostly what I'm familiar with, which is QBox, but that applies to a number of other codes as well. Basically, what you have to do is distribute the load, distribute the work. Okay? So assume that we're looking at our matrix Y here. That's this matrix here. And so there has the index of the rows is G, the G vector, the plane wave index. And N here is denoting the number of states. And I just take the general case where I have several k points. So I would have multiple copies of this matrix Y at different k points. So what I can do is I can cut that in blocks and distribute that matrix over different processors. And now try to organize the code so that it will work on these separate blocks at the same time. Well, what happens if I have a single k-point wave function? Okay, so let's ignore the multiple k points for now, and we can come to that later. But just to simplify the presentation, we'll consider just one such matrix here. So remember, we were talking about the matrix that would work on 10,000 electrons with 10,000 states and about 1 million plane waves. That's for very large problems. And let's consider what happens if we use a large number of processors here. That would be about 8,000 processors. So that we would have a grid of 500 in that direction. So the number of blocks here would be 500 and 16 blocks in this other direction. Now that's the kind of thing we'd like to do now with parallel code. So let's see what the communication patterns would be in the parallel machine if we do that. So first of all, we would have these three-dimensional Fourier transforms to perform. whenever we compute the charge density from the wave functions, or whenever we solve the Poisson equation. So what happens here is now we would have the Fourier coefficients of the wave function distributed over many processors. So whenever we do Fourier transform that involves these coefficients, then it would have to be communication among those. Okay. But not between columns, so that's critical. So this is one way in which we can organize the work so there's not too much communication. There's communication in one direction of that grid, but not in the other of that one. Then there is what happens when we accumulate the charge density across all the electronic states. Well, that's a different pattern of communication. Here now we have some bit of the charge density for these wave functions in some region of space, and all the contribution from other wave functions in the same region of space, and we want to sum them up, and the sum will go across that direction. So this is typically the kind of strategy we try to use to make it feasible, to make it scalable, is to avoid communication that goes all over the place at the same time. We try to orchestrate the communication so that it's only a limited number of nodes that talk to each other at any given time. Well, then there are other operations where we can't avoid that. So these are the cryptic names of functions of the scala-pack library, which is what does linear algebra and parallel for us. And things like the orthogonalization, computing the non-local potential energy, computing eigenvalues and eigenvectors. This is just the whole machine talks to all nodes all over the place. So this is more difficult to scale.
So communication at the same time in different places, does it create any conflict?
Well, that's for the hardware of the parallel machine to take care. We assume that the communication library can deal with it. Basically, what happens in practice if there's too much communication along the same lines is that it waits. So there's a bottleneck, and that will slow down your calculation. So if you organize the communication in such a way that there are not too many traffic jams, basically, you tell everybody in your city to drive east-west at a given time and north-south at another time. Nobody crosses the intersection, okay? Obviously, this is a cartoon. I mean, it doesn't happen like that in a computer, but this is a way of limiting traffic jams. So then there's another question, which is if you're going to use this kind of decomposition of tasks in a rectangular grid of processors, well, you then have to think of how that maps onto the actual machine, which is connected in a physical way, which is not necessarily that one. So if you look at what happens in a Cray XT, for instance, it's a torus network. So you have to map your processors from your logical grid to a physical grid. So there's some simple ways of doing that. So suppose that you map the first column onto the first processors that you find, and then you keep going this way, so the second one keep filling up, and so on and so forth. But quickly you realize there are many, many ways of doing that. So what I'm showing here is these kind of mappings of logical to physical nodes that we used on a calculation that Lawrence Livermore lab in 2005. And in that case, we were using the Blue GNL machine that has 64,000 nodes. And we had this problem of mapping our logical problem to a torus, which is actually a kind of an orthorhombic torus type. And we found that we could try all these different mappings of logical to physical. And in some cases, that meant there was a huge difference in performance. So this is kind of a new frontier in parallel programming, if you wish. You don't not only have to worry about how much communication is taking place in your program, but now you have to worry about how you're going to map your parallel process to actual physical hardware and optimize that. So that's another level of optimization. And that's the kind of the naive, simple distribution of column that I've shown on the previous slides. Now, you would think that maybe it's a good idea to have each column reside in a smaller region of the machine. It turns out that this is the best way. And it's completely non-obvious. So the only way you learn that is by trying. So it's kind of an interesting new direction.
I mean, doesn't this presume that you have contiguous nodes? And also, what about the problem that, I mean, your interconnects are going to be different on different machines?
That's correct. So your optimized mapping will be true for one machine, will be good for one machine, not necessarily on another. In the case of BlueGenie now, this is actually contiguous node. Yes. This is a correct view of the machine as it is. So each little square here is a node and has a connection to its neighbors. But it's true that if you find a good way of doing this on one machine, it doesn't mean you're good on another machine. Okay, so this is just to give you a glimpse of the kind of issues that come up when you start using large computers. Having said that, let's look at a few examples of how that scales in the end. Everything is said and done. This is an example of what's feasible currently with Qbox, for instance, and this is an example where we compute the electronic structure of a silicon nanowire with more than 2,000 atoms, and that's done on the Great XT4 at Lawrence Berkeley Lab, the NERSC facility. And we find that we can scale reasonably well up to something like 8,000 processors. And you notice here that the ideal scaling curve here is the red one, and the measured scaling is the green. And you might wonder what it means to be better than ideal at this size. And it actually happens, and the reason is simple, is that as you go to the same problem distributed on more processors, you have less data on each node. And you also have less data to work on each processor. And what that means is also that you are in a situation where that data now suddenly fits in the cache of your processor. So your processor gets faster. So it's kind of an indirect effect that makes it possible to actually be better than linear in that speed-up curve. Usually it doesn't get much better. This is possible. It will not go much better than that. So this is the kind of result we get, 86% parallel efficiency over that range. It's nice. I mean, it means that you can really basically reduce the time to solution by 2 if you go from 2,000 to 4,000 processors. 8,000 starts seeing some problem, and beyond that, it's not as good. That's other same kind of data on another machine. So that's a large machine at the Texas Advanced Computing Center, and that's another one. We always use the same kind of benchmarks everywhere. This is also going to 8,000 processors on the BlueGenie computer at Harvard National Lab. How well do we use the computers is also a question you should ask. These computers are boasting teraflops of computing power, and you may worry that even if your code is scaling well, are you actually using this computing power that you're at? So this is the history that we have gathered on the performance of first principles molecular dynamics code over the years. And it's interesting to see that we started back in 1985 with Carr and Parrinello and their Cray 1 and their machine that was looking more like a VAX. I don't know if any of you in the room remember what a VAX is. It's a very small computer at today's standards. And on that period of time, the achieved performance of first principles molecular dynamics code has grown exponentially, roughly, following that curve. And it basically the performance has doubled every 8 months, which is faster than Moore's law. Moore's law is the doubling of actual number of transistors in a chip every 18 months. And we can go faster than that because we're using more and more processors. We're using more nodes, so we can also grow faster than Moore's law. And this is the number we did on BlueGenie machine in 2006 with Qbox. So we're basically going with this line that's exponential growth. So if you look at this number here, the million gigaflops is the petaflop, and it looks like we're going to be there soon. But that's a little bit deceiving because this last stretch here is actually very difficult. We'll discuss why at this point. these new computers are looking bigger and bigger in terms of their computing power, but look at more details about their characteristics here. Those are this current generation of petascale machines that are appearing, have appeared already. So there's a machine that I showed you some tests on, 8,000 quad-core nodes. That's actually outdated now. They've upgraded that to a larger now. Kraken is what you used yesterday. So you could have used more tasks. There's more behind there. But on the small problem that we had, it wasn't really worth going beyond eight tasks. The TSCC Ranger also is a pretty large machine, 500 teraflops. The current BlueGNL at Livermore, maybe I'm wrong, some people from Livermore would correct me here, certainly beyond that number. Anyways, one thing that you should look at here is that the number of processors here gets larger and larger. So in the last case here of the Roadrunner at Los Alamos National Lab, we're talking about 122,000 CPUs, and they reach beyond a petaflop. So basically what it means is that we have to deal with more and more processors to get this large power. So
it means that to publish a realistic thing in PRL or in Nature or NanoWire, you cannot do if your country do not have this facility. It's very, one-to-one mapping, because those kind of paper is going to fall in the hand of you, and definitely it's obvious.
Well, I think you're right. In some sense, although I'm not sure that what makes you publish in PRL or Nature is entirely based on the computing power. Often it's not the only factor. And I guess, unfortunately, the fact is that if you are in this situation, pure numerical work is a difficult way to go. That's a resource that's necessary, and unfortunately, in the case of first principle simulations, a huge amount of computing power is necessary. Not only to run the simulation you're going to publish, the simulation you're publishing is 5% of your computer budget. On the 95% other part is all the verification that you've done to make sure that you're at the correct answer. So if your budget is limited, then that's a difficult way to go. I totally agree. So basically, all this discussion about number of processors and huge machines, it sort of leads us to kind of reflect on the limits of computational efficiency that's achievable. And let's just go through some basic timescales here that are involved in computing on today's machines. First timescale is how long does it take to perform one floating point operation, be it a sum or a multiplication, and that's on a modern processor like the Opteron at 2 gigahertz. One floating point operation would take 0.125 nanoseconds. Now compare that to the time it takes to get a double precision number from memory, which is about 4 nanoseconds in the best cases, and get a double precision number from another node of this parallel machine, which being really optimistic would be 8 nanoseconds. So you see that there's already a big mismatch between the time it takes for you to do an operation on a number